Okay, hello everyone. Welcome to today's lecture. Please confirm that you can see the screen and hear me clearly. Thank you. Thank you for confirming. In last lecture, we were basically talking about our target is to write assembly language programs for ATmega 328P, and towards that target, we started first talking about understanding the basic instructions, very simple arithmetic instructions, which is add, sub, or loading some immediate number into a register through LDI instruction, or loading data from memory into a register through LDS instruction, or from a register into the memory through SDS instruction. We also had a look at division of the our dividing that address space into four different segments, and we also had a look at instructions in and out, which can be used to move data to and from the IO registers, right? So, besides that, we also had a couple of example, or actually, I think we had only one example about how the value of carry flag, zero flag, and half carry flag in the status register is affected as a result of arithmetic operation. For example, addition, right? So today we will start from the same point. So. I think we did this example, but let me repeat it to refresh your memory, right? So we were basically talking about the status register, and we said that status register has 8 bits, and each of these 8 bits they have their own significance. So, but for now we are focusing only on the carry flag bit, zero flag bit, and the half carry flag bit, right? And these bits they are affected but they are affected when certain instructions are performed. For example, add instruction or subtract instruction, also other instructions, they also affect the value of these bits. For a complete list of the instructions which affect the value of these flags, you can go to the appendix. Uh, I don't remember the name of the appendix, but you can go to towards the end of the textbook and you can find there the detailed description of each instruction, and they also mention whether the given instruction affects the value of the flags in the status register or not. Okay, so here is an example which we use basically to understand how the value of carry flag carries C flag, H flag, and Z flag is affected, right? So here we are adding two numbers. We are actually executing this code. So in this code, we are loading 38 into R16 register and 2F in R17 register. And these numbers are in hexa. So I'm not reading 0x, I'm just directly saying 38. And when you execute this add instruction, then as a result of addition, the value of these flags will be set depending upon the result of addition, right? And how the values set. So for that, we did this example. So when you add these numbers together, what you will see that there is a carry from the bit position 3 into bit position 4, and there was no carry out from the bit position 8, out of the bit position 8, and the result is not 0, right? So since there was no carry out from the most significant bit position, that's why the carry flag is 0. If we had a carry out from the most significant bit position, we would have the value of 1 for the carry flag. Similarly, since we have a carry out from the bit position 4 into bit position 5, that's why we have the half carry flag set equal to 1. So the hardware sets it out automatically. You don't need to worry about it. As a result of depending upon the result of the addition, these flags are set by the hardware of your microcontroller automatically. And since the result of this add instruction was not equal to 0, that's why Z flag is equal to 0. If we had a result which was non-zero, then we would have Z equal to 1. Okay, now let's have a look at another example. Let me first erase this stuff. Okay, so here in this example, you need to show the status of the C, H, and Z flag after the addition of 0x9c and 0x64 in the following instructions. Now, is everyone clear on the previous example? If you are not clear, let me know, because now I want you to do this example on your own. So if you are not clear how we did the previous example, let me know. Okay, it seems like everyone understood. So then go ahead and you have 1 minute to solve this example. Thank you. Thank you for confirming. So I am also doing on my notebook. Okay, thank you. Yeah, let's wait for some other people to complete. Nice. Okay, so then let me walk you through the example here. So when you will do the addition, so you will get the result where you have the result will be all zeros. The first bits will be zero, the most significant ninth bit will be 1. But since we are assuming that we can store only 8 bits, because in ATmega 328P, all the registers are 8-bit registers. So since we are assuming we can retain only 8-bit result, so that's why we focus, when we say result, we will focus only on the first 8 bits, right? So since all the least significant 8 bits, all 8 bits are 0, that why our Z flag will be 1. And when you do the addition, you will find that there is a carry from the bit position 4 into bit position 5. That's why your half carry bit or half carry flag will be set equal to 1. And there will be a carry out from the most significant bit position, which actually is represented here, right? So that's why your carry flag is also will be also set equal to 1. Okay. If if you are not clear on the result, or if you got a different result than what is shown on the slide, let me know and I will explain in more detail. Nice. Mm. So it looks like everyone is clear on this example, and I am proceeding to the next slide, okay? Okay. So here is another example. Let me again erase the markings. So here, now you need to show again the status of C, H, and Z flags after the subtraction of 0x23 from 0x5. I think let me do this for you, because this is the first time you will be doing a subtraction maybe. So it's better that I follow you through this example, right? So when you actually execute this code, what will happen? You are first loading A5 into R20, you are loading 23 into 21, and then you are saying subtract the value of register content of R21 from the content of R20, right? And the result will be stored back into R20. And based on the result of this addition, this subtraction, your flags Z flag, C flag, and H flag, they will also be they will be set according to the result, right? So first we write A5 in the binary form. So the binary of 5 is 0101. The binary of A is 1010, right? We do the same thing with 0x23. So the binary of 3 is 0011 and the binary of 2 is 0010. Now we need to do subtraction. So how we do the subtraction in binary, subtraction between subtraction in binary numbers, right? So first you subtract like this one from one, you will got 0, no problem. Now in the next position, we need to subtract 1 from 0, but we can't do that, right? So we take a carry, right? We take a borrow, right? Now, if you remember, when you are doing subtraction when you are doing subtraction using decimal numbers and you need to take borrow, then what amount is borrowed? It is the base of the system. In decimal, it is the base is 10, so 10 is borrowed. Here, what is the base? Base is 2. So when you borrow, so it's mean you are borrowing 2, right? So when you borrow 2, what will happen is, and you borrow 2 and the position from which you are borrowing the number, it is reduced by 1, right? So what will happen that this bit position at 3, it will be reduced to 0 and we are borrowing 2 here. So 2 minus 1 will be 1. And then in the third bit position, 0 minus 0 will be 0. In fourth bit position, 0 minus 0 is 0. In fifth, 0 minus 0 is 0. 1 minus 1, 0. 0 minus 0, 0, and then 0 minus 1 will be 1. Okay. So this is the result of subtraction here, right? Now, there was no borrow from the fifth bit position into the fourth bit position, no borrow, right? And similarly, there was no borrow in from the borrow in into the most significant bit position, right? So that's why our carry flag is 0. Why? Because there is no borrow in the most significant bit position. Our Z flag is 0. Why? Because our 8-bit result is not 0, right? And H will be equal to 0. Why? Because there is no carry in, borrow in from the 5th bit position into the 4th bit position. So this is how the value of C, Z, and H flag will be set. Is everyone clear on this? Okay, so, okay, thank you. And so now go ahead and do this example. So where you are doing necessarily the same thing with only difference that different numbers are used for performing the operands are different. Okay. You need to find value of C, H, and Z flag after the subtraction of 0x73 from 0x52. And you have 1 minute. Okay, done, 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 done. Okay, I was a bit slow on this. So, okay, let's have a look at the solution. Okay, so yeah, okay. So again, we do exactly the same thing. We write 0x52 into the binary form. The binary code of 2 is 0010. Binary form of 5 is 0101. We do the same thing for 73. The binary form of 3 is 0011 and of 7 is 0111, right? Now, when you do the subtraction, you do exactly the same way which I explained earlier. We cannot subtract 1 from 0 in the first bit position, so we take a borrow. So when we take the borrow, we get 2 here. But remember that the place from where we are borrowing, it is reduced by 1. So if it is reduced by 1, we are left with 0 here, right? So 2 minus 1 is 1. Now we cannot subtract from 1 from 0, right? And we cannot also borrow from the next position because it is 0. The next position is also 0. The next position is 1. So we take a borrow from here, right? And the value here is reduced by 0. The borrow we take is 2, but then we need to take borrow towards the next position as well, right? So this is reduced from 2 to 1. I mean, and this position, we take the borrow of 2. And then we take the borrow again to the next position. So this is reduced to 1. And here we have the borrow of 2. So 2 minus 1 is 1. 1 minus 0 is 1. 1 minus 0 is 1. And here we were left with 0, right? So we cannot subtract from 1 from 0. So we do exactly the same thing again. We start borrowing from the next position. So eventually you will get the result 1101. And when you will do the same process, you will see here that you need to get a borrow into the most significant bit position, right? So that's why which will be later dropped like to 1. That's why we will get 1 minus 0. Okay. So when you will look at the results, so you will have C is equal because we are getting borrow into the most significant bit position. So that's why carry flag will be set equal to 1 since our 8-bit result is not 0. So that's why Z will be set equal to 0. And since we have a borrow from the bit position 5, fifth bit position into fourth bit position, that's why half carry flag will be also set equal to 1. Okay. So the H flag is only if it borrows from D4 to D3. Yeah. So H flag is in subtract operations. If it borrows from D4 to D3, then H flag is set equal to 1. In addition operation, if there is a carry from the bit position D3 into D4, then also the H flag is set equal to 1. Okay. You're welcome. Okay, again, there is another example. Go ahead and do the example while I'm getting rid of these markings. You have 1 minute. Actually, you you can do it in 50 seconds, right? Okay. Yeah, nice. Thank you. And let's have a look at the solution here. Yeah, so the both numbers are same. When you do the subtraction, you will get the result of all zeros. There will be no carry, no borrow in into the most significant bit position, and there will be no borrow in from D4 into D3. So that's why our C will be equal to 0, our H will be equal to 0. However, our Z will be equal to 1 because our result is all 0 bits. Okay. Yeah, nice. Okay, so how these flags are now used. Actually, here it is only like kind of information. We are not going to in detail of the procedure, how these flags are used. But here we are just giving the information that these flags are used when your AVR microcontroller executes the branch instructions. So branch instructions are like kind of conditional instructions as written here. For example, branch if low. So in this, what does this instruction do? It actually tests the value of C. If the value of C is equal to 1, so then the branch will be taken to the given destination. Okay. Now, at this point, don't worry about how these instructions work. We just what we want to highlight is the following, that all of these instructions, they use one of these value of one of these flags. For example, branch low, it tests the value of C for 1. Branch if same or higher, it tests the value of C for value for 0. Branch if equal, it tests the value of Z flag for 1. Like if the value of Z is 1, then it will take branch to the destination, given destination. The program will branch or it will go to the given destination and so on, right? And here it has these flags, N flag and overflow flag, which we have not yet discussed, but these flags are also used in branch instructions, right? Actually, there are two type of branch instructions uh, here, which I'm drawing the line to divide them into two groups. This first group is for when you use the branching, when you want to use branching based on the unsigned numbers. And the second group of instructions is also used for branching, but when you want to use uh, signed numbers for comparison. Don't get confused. I just wanted to highlight like there are two groups. Okay. We will talk about more details about branching based on the signed comparison of signed numbers and comparison of the unsigned numbers. Okay. So this is same example. I'm just skipping it. Okay. So now we have seen how the value of Z flag, C flag, and H flag is set as a result of, for example, add instruction or subtract instruction, right? Now, in the next couple of slides, we are going to talk about assembly directives. Previously, we were talking about assembly instructions, right? So here we are talking about assembler directives. Directives are not instructions. What are instructions? Instructions are like the operations which are executed by your hardware, which is in our case microcontroller at Mega 328P, right? Assembler directives are not instructions for the hardware. They are actually instructions for your assembler software, the assembler program, right? When you write the program, you write the program, for example, let's say using the assembly language, and it is the job of the assembler program to convert your assembly program into machine code. Remember, every instruction is converted into the binary form, just like we had seen in previous simulations, right? Who does that? Assembler. But then sometime we need to give some information to the assembler or some directives to the assembler. How? By putting directives in our assembly code or in an assembly program, right? And the first two directives we are going to talk about are equate directive and set directive. Okay. So what is the syntax of equate directive? So its syntax is you just put this dot EQU. You note that you need to put dot. Directive starts, all the directive starts with dot. Okay. And then after that, you put the name and the value, right? So what is the meaning of this directive? So you are basically saying that you want to equate, uh, you want to define a constant and set it to a value. For example, here when you are saying dot equate count comma 0x25. So you are saying I want to equate count with 0x25. It is just like if you have used the assembly, sorry, C or C++ language. Just like in C or C++, you define macros, right? So it is same as that. So here, now what will happen that everywhere in your program where are you using the count, it will be replaced by 25. So when assembler will convert your program into the machine code, it first will replace this account with 25 and then generate the machine code of this instruction. Similarly, it will replace this count by 25 and then add 3 to it, which will become 28. So the instruction which will be converted by the assembler into the machine code will be load immediate R22 comma 28. Okay. Okay. So, and the other thing is that one thing about dot equate directive is that once you have defined the macro, right, later on in your program, you cannot modify it. You cannot say, I want to change the value of count from 25 to, let's say, 28. Okay. But if you want to do that, then you need to use a different directive, which is dot set. So dot set actually does exactly the same thing as equate, but it provides you the flexibility that you can update that macro in your code at a later point. So for example, let's say initially you said dot set count zero count comma 0x25. So everything is same as in this example, right? But here we are now allowed if we want to update the value of dot set count 0x19. So in these two instructions, the value of the count used will be 25. So the instruction will be load immediate R21 count, which is 0x25, and load immediate R22, which is 0x28, right? But after this second dot set directive where we have updated the value of count to 0x19, where we have set the count to 0x19, now we in this instruction the updated value, which is 0x19, will be used. Okay. If we were using dot equate, we cannot do this. We cannot write here that the second statement dot equate count comma 0x19. Okay. So if you do, the assembler will complain. Any questions? So what is the yes, yes. So, like if you are writing a program and there is some value which you are using at multiple places in your program, but that value is a constant and you are short sure that you will never change it in your program everywhere, anywhere. So, what you can do is like to increase your readability, you can define it at the start, like using dot equate count 0x25, right? And other feature is like, let's say in first run of the program, you want to test your program by using that constant value of 25. In the second run, you want to test the program by setting the value equal to 100. So if you were not using equate, you need to change the code at all places where you had placed the 25, right? But if you are using equate, you just need to make change at a single place. Okay, the next two directives which we are going to talk about are dot data and dot text. But before I talk about that, remember we have two different memories in the AVR microcontroller. One is data memory, which I'm just writing as DM to indicate data memory, and the other is the code memory, right? So in code memory, the code is placed and data memory data is placed, right? So uh, what is the job of this dot data directive? So it basically it tells the assembler that whatever comes after this directive, whatever in assembly program I'm writing after this directive, put all that in the data memory. Okay. And what is the job of the subsection? So the this next part in the directive. So actually, the data memory you can define, you can you divide it into different sections or different sections. Like for example, you want to name the first section as A, the next one as B, right? So what you can say is like if you write here dot data A, so it's mean like whatever I'm going to write, put it in the memory, and the area of the memory where you are putting it, refer it as section A or subsection A. Why we use the subsection? Because data memory is considered itself as a section and code memory as itself as a section, and then the sections within the data memory, they are known as subsections. So we are telling the assembler to assemble the following statement onto the end of the data subsection numbered subsection, right? So if like previously we had, let's say, the subsection A, and then after that here, and then after that I put the code, I put the directive dot data B. So now I'm saying that whatever I'm putting here, whatever instructions or whatever I'm writing here, that needs to go in B, right? And if after that I say dot data C, and then I put something else again here, then that will go into the data section C. Okay. Any questions? I'm raising these, but if you have any questions, please write me in the chat. Why would you want to do this? Okay. One of the student is asking that why we want to uh, use the data directive or tell the assembler to put a specific whatever we are going to write in the program in the data section or in the code section. Anyone who want to answer that? Like what are uh, your first thoughts about that, about this question? If you want to answer, you can unmute yourself and you can talk. Because remember, yeah, that's true. Give direction to the assembler, but like, what is like more deeper explanation to that in sense of like the architecture, right? Remember we said like there are so you can keep using it without having to write out the code every single time because this stuff can be changed at runtime. Uh, Thank you for at least giving it a try. That's a nice thing. But let me give you a more correct answer to that. So remember the ATmega 328P, it has separate code and data memory, right? So whatever you are writing in your program, you need to tell your assembler where it should go, the program you are writing, because your program will contain two things fundamentally. It will contain the data and it will contain the code, right? But assembler is unable to identify if you don't specify whether a given set of statements in your program are they indicating the code, are they indicating the data, right? Because just like in C or higher level languages, for example, let's say you need to first declare the variables, right? So where do you declare the variables? They should go to the data memory. Or where you declare an array, it is a data, right? So it should go to the data memory, right? So but assembler doesn't know that it, but just by looking at the statements in your assembly program, that whether they are intended for the data memory or for the code memory. That's why you put this directive dot data, right? So even you can omit this subsection part. If you don't want to maintain subsections within the data memory, you can just write dot data, and after everything written after dot data will go to the data memory. Okay. I hope you got the answer. Okay. If subsection is omitted, it defaults to zero. It defaults to zero mean there will be no subsection, and like there will be only one section in the data memory, and all the declarations you make, like to declare the variable or arrays or any kind of data structures, you want to, let's say, reserve the memory. So all of them will go to the, they will be like all of those statements which actually do the actually reserve the memory or for variables or data structure, they will be pointing to the they will go into the data section, data's memory. The text subsection, so it's same, but only for the code memory. So here you are basically saying that whatever I write after this directive, it should go to the program memory. So you are basically saying that now I am writing the statements for my code, and that after dot data, whatever statements you wrote, they were for your data. So assembles the following statements onto the end of the text subsection, numbered subsection. Okay, this is same as what I explained. The only difference is that now we are talking about code memory. And if you can also omit the subsection part, you can only put dot text, which means you will have only one section in your code memory and all the code will go in there. Okay. Any questions? Okay. The next two directive we are going to cover are .com and .global, right? So .com basically it is the short form of common. Okay. And it is same as the concept of a global variable in C or C++ language, right? So what is global variable? Global variable is one which is like visible to all different functions. Let's say you have a multiple functions in a program, and then you define a global variable in that same program. So all those functions, they are able to see the global variable, right? They have access to the global variable. So here we achieve the same effect by using the directive.com symbol length, right? So what is the like this is the syntax, right? And what is meaning of it? It actually declares a common symbol named symbol. So you are saying that whatever symbol or whatever variable I'm declaring here, it could be variable or it could be a name of a function, doesn't matter, but it will be a symbol. It can refer to a variable, it can refer to a function or part of a code, right? So you are saying that it is it should be visible to all the code within my current file, right? So let's say you have a single file here, file or a single file in your program, and you are writing here some code, right? But at top you said .com and .com X, right? So now X, you can use this X as a symbol anywhere if you use it anywhere here in your code, it will be usable. Assembler will not complain. Okay. And length part, allocates the length byte of uninitialized memory. Uh, uh, Length must be but the length must be an absolute expressions. For example, if you write .com x 2, right? So what it will do is that it will reserve 2 bytes of memory but uninitialized, which mean that it will have garbage mean we don't know whatever the memory previously contained, it will be retained there, but 2 bytes will be reserved, and those 2 bytes will be given the name of x, right? So if you have, this is, let's say, the memory, right? And you reserve 2 bytes here, and those 2 bytes are collectively given the name of x, right? And then this x is visible in your code anywhere you can use it. So anywhere you put the x, you will be actually uh, you will be referring to the address of the first byte in sequence of these 2 bytes. Okay. So multiple common symbols with the same name allocate space using the largest size. So like for example, if say common x comma 2, and then put another direct other statement dot common x comma 10. So which one of them will take effect? It will be the one which has the largest size, which is dot comma x comma 10, right? Any question about common symbol or any confusion? Common directive? Any confusion or question before I go to the dot global directive? No? Okay. So dot global directive, it is same as extern in C or C++. For those of you who don't know how extern work in C or C++, so it is basically here we were defining a global variable which was visible to all the functions in the same file, right? So let's say you have here function 1, you have function 2, and here you have some global variable x. Both functions, they can access the variable x. However, if your program consists of multiple files, let's say this was your file 1, right? And this is your file 2, right? And in file 2, if you write a statement which says, let's say x plus plus, right? So your compiler will complain. Why? Because x is not defined in file 2, it is defined in file 1. So what you do, you use the variable extern before x, right? You tell the compiler that it is defined in some other file in my program. So we do exactly the same thing to achieve the same effect. We use the directive dot global in the assembler for the assembler of the ATmega 328P, right? So for example, if you say dot global x, so you will be telling in this file, for example, in F2, if you sorry, in F1, if you here you write dot global x, you will be telling compiler that okay, make this symbol visible to the code also in other files. If you have a program consisting of multiple files, then what will happen that your symbol will become visible to other files as well. So if defined in the current file, it makes visible to the other files. Okay. Otherwise, if it is not a current defined in the current file, symbol takes as attribute from a symbol of the same name from another file. Is it clear or not? I think we have examples, so it will become clear to you. Let me walk you through the example, and then if you have questions, I can take those questions. So in this example, let's say we first want to define we are defining two variables, val1 and val2, right? And we are making them the global data, right? So we are writing first dot data is the directive. So here we are basically going to say whatever we write in our assembly program after this statement that needs to go to the data memory, right? And first we are saying dot comma val1 comma 1, which means what? Which means that dot com is we are defining a symbol which should be visible to all the code in this file, right? Which we are writing, right? And then and here one we are putting comma 1 to mean that reserve 1 byte in memory, in data memory. In data memory, reserve 1 byte. Don't It is uninitialized, right? And give it the name of val1. So basically, if you want to talk in terms of like higher level languages, you are making a you are declaring the variable, right? The variable of size 1 byte. Okay. And when you say dot global val1, now you are saying, yes, we have already declared a variable of size 1 byte, but now I want to make this variable visible to the code also in other files in my program. Okay. We do the same thing for another variable val2, value2, which is also 1 byte location in memory, and we are naming it as val2, right? And then we are saying dart global val2, which means we are telling the assembler to make it visible to the code in other to the code in other files in the same program. Remember, one program can consist of possibly can consist of multiple files. Okay. After that, we are starting our code segment, and that's why we are putting the dot text. So when we say dot text, which it means whatever I'm going to write here, it should go to the code memory, not to the data memory. Okay. However, the code that I will write here, it will be able to refer these variables val1 and val2. Why? Because I already gave the directive to the assembler that make these variables val1 and val2 visible to the code, to the whole code in this file, and also to the code in other files, because I put the global as well. Okay, here in again, I'm using the dot global. Why? I'm using dot global compute. I'm basically saying that the name the okay. First, let me talk about this thing. Compute followed by a colon. So when you have any name followed by a colon, it is called a label. So label is basically point to a certain instruction in the program. So basically, we are saying that this instruction in the program compute, or this label compute refers to this particular instruction in the program, or this particular point in our program sequence. Okay. So what we are saying here, dot global compute, it's mean that make this particular point in our program visible to other to the code in other files as well. Okay, so if you have another assembly file and it then it can refer and it uses the word compute, so it's mean that it is referring to this point in your program. Okay, so it is just like function. Okay, function in terms of higher level languages. So if the other program calls compute, so the code starting from this line will start executing. Okay, and after this label we are saying, okay, load the value from memory location or memory address val2 into R12. See, we are using LDS instruction. What is the meaning of this instruction? This instruction says move the value, copy the value from a memory address into a register. And note here, we are not using the address. We are using what? We are using the symbol val2. What is val2? Val2 is name of this byte in the data memory which we have already reserved using dot common directive. Okay. So now we can give names to the memory. We can refer to the memory location using variable names instead of using the absolute memory addresses. And definitely it increases your readability of your program. And then in next instruction, we are saying, actually here it should be LDS, not LDI. Let me correct it right now because then I will forget otherwise, right? Okay, so then here we are saying that load the value from memory location which is named as val1, right? Here we have already, we said reserved 1 byte in the memory and gave it a name of val1. So load the value from that memory location into register R19. And then we are saying add R18 and R19. And then we are saying store the result from R18, which holds the result of addition, into the memory location named as val1, which we already reserved, right? And then here we are saying return. Return mean it is just like this is a new instruction. We will talk about more detail about this instruction later on, but here we are basically saying return the execution control to the function which actually called this function. Remember we said that label can be used as a function. So for example, if you have a function here, f1, and in the body of this function you have some code here and it says compute here, right? So when it says compute, so after first these three instructions will be statements will be executed, and when you say compute, or basically you will say call compute, not only compute. So when you will put call compute, after that these instructions will start executing, and when you go to reach the execution control reaches return, then after that then instructions at the bottom of the call compute, they will after the call compute they will start executing, okay, in the sequence. So that's why, so this instruction is basically returning the execution control back to the caller function. Any questions? Okay, so here in this example, until now we have, does the indentation matter? No, it doesn't matter for the purpose of correctness. I mean, whether you do the indentation or not, your program will still work as long as you, like, for example, you at least put at least a single space between, like, for example, LDS and R18, and for example, between compute and LDS, right? However, doing indentation is recommended because it increases the readability of your code. Uh, Okay, so in this example, until now, we have seen a single file, right? It's assembly file. In that assembly file, what we did, we defined two variables, val1, val2, each of byte size, each of 1 byte size, and then we, in the program code, we actually wrote a small program which reads the values from those two variables, adds them together, and put the result back in the variable one, and then it returns to the caller, right? Now, but we are not done with an example. In this example, we are going to write multiple files. So this was our file one. This was our code in our file one, right? So when you do the programming in AVR, like uh, for example, in lab one, you use Arduino IDE, right? And remember, I said you don't need to worry about the code in that lab, which was written in .s file or assembly file, right? However, I hope that you have realized that you had two files in the lab. One was .ini file, which actually contains your C code. The other was .s file, which contains the assembly code, right? Now, how we link these two files together. Linking mean in the sense that the code written in the .s file, how it becomes visible or how these two files work together as a single program, right? So we are going to talk about that. So remember, in the previous file, we have declared, we have these variable val1 and val2, right? Now, when we are going to write the code in C for the Arduino IDE, we'll be writing it in .ini file. And we want in this file we are going to make use of variable val1 and val2, but val1 val2 they are not defined in this file. They are defined in the first file. Let me name it as I don't know, let me name it as f1 dot s. Okay, so they are defined in f1 dot s file, right? But we want to use them in let's say I'm naming this one f2 dot ino, but I want to use the symbols which are defined in f1.s file in my f2.ini file. Like for example, variable val1, val2, and compute. I will be using them, right? So first I need to tell my assembler that these symbols, I'm writing the program in C, right? And that's why I need to use the keyword extern to tell my assembler or my compiler that these variables val1, val2, they are defined in another file within the same program, right? So, and compute is also defined in another file, right? And here I'm just basically saying extern C void compute. So I'm using like C language. So I want to give that information. And I'm also telling that compute val1, val2, they are defined in the other file. So go and check in the other files. So extern this symbol exists it is basically giving the following information to your compiler that this symbol like val1 symbol, val2 and compute exists somewhere else. Don't allocate new storage for it here, just reference it. And this is the so for first writing this code, we are going to write this function in our .ini file. What is the function? Read two digit values. So this function basically what it will do, it will read a two-digit decimal value from user. So actually, I guess in future labs, when you will use it in future lab, you will become like you will understand it more clearly. So here what we are doing is in this function that we are first defining a variable inch of type byte. So we are saying that it has a size of 1 byte. We have another variable with name of val and its type is int, which means it will occupy 4 bytes in the memory. Now serial.println enter a two-digit decimal value. At this time point, you don't need to worry about it. We are only using it in our program, but that's not focus of our today's slides, but we are just putting it here so that we can make our example to work, right? So what it will do, it will basically, when you will run this program on your Arduino IDE, there is a console which is known as serial console, I guess. So this line or this message will be printed on your terminal or on that console, and it will say enter a two-digit decimal value, and then it will wait for you or user to enter two digits, right? So how the program will wait by executing this while statement. Again, you don't need to worry about this one, right? So because we are not learning how to program in C language, we will be learning how to program in assembly language. But this function will be only helpful to read the values from that console, right? So when you will press any button, let's say you press 1, right? So let's say you want to enter two-digit value, and that two-digit value is, let's say, let me give you the number 23. Okay, so you press 2, right? So first you press 2, so it will be waiting for like 100 time units, and then it will read the key. So as you press 2, it will read it in the inch, right? So but remember, whenever you press a key, what is read by your hardware? Anybody who want to tell me? When I press 2, character of 2, what will be read by hardware? The ASCII code of that character, remember? So when you press 2, the ASCII code of that character will be read, right? And it will be placed in what? It will be placed in inch. Now, what is the ASCII code of 2? Let me show you. I think we had it in first slide. No. In the second slide, still not. In third, I guess. Yeah, here. So uh, what is the code for character 2? It is 32, right? The hex code is 32 here. When I press 2, the 32 hex code will be read, right? So now let's go back to our example. Let me check the time. So you also have the quiz, but we have some minutes. I can try to complete this example. So when you, let's say you press, what was our number? Our number was 23. So when you press 2, the serial code, ASCII code of 2 will be read and saved in inch. What was that code? I guess it was 32, right? So then in next statement, you are saying val is equal to inch minus 0 within single quotes. So when you say minus 0 in single quotes, it's basically you are saying subtract from inch the ASCII code of 0. The ASCII code of 0 is what? It is 30, right? So you are basically saying 32 minus 30. So which is equal to 2. And then you are multiplying it with 10. So what will be the value of val? It will be 20, right? And then this program will again wait for 100 time units, and then it will read the second character which you will press. In this example, it will be 3, right? So it will read it, and it will place it in inch variable, right? So then what is the ASCII character of ASCII code of character 3? It is 33. Uh, right? And then what does it do? It does val plus is equal to inch minus 0, right? What is inch? Inch is 33 minus ASCII code of 0, which is 30. So it becomes what? It becomes 3. What is val? Val is 20. So here you are saying val plus 3. So it becomes 23. So then the value of 23 is stored in this variable val, right? And then you are printing the value. So this language basically again print on your console this message. The value entered is this value, whatever value is this one, and here you are specifying the base of the value 23. So you are basically, this line will print 23, and you are saying that the value I'm specifying is in decimal system. Okay, so it will print the value, it will print the message, the value entered is 23, right? And then it will call return byte val. But this is, let me see if I made an example. I made a Yeah. So and this will basically return the control to the caller function, the function which is calling this one, read two-digit value, right? So let me stop here and ask if there is any confusion about this function, about the about how this function is working. Yes, I know that you may not completely understand how these statements are working, right? Serial.println and this one, but don't worry about them. If you are clear on how the value is read, like for example, what is this inch is equal to serial.read and what is this mathematics performed here, then I'm fine. I mean, I'm fine with your that level of understanding. Okay. Okay, if no questions, I'm assuming no question because I didn't get a response other than saying that everything is clear. So I am moving on. Let me check the time. Uh, so we have like 5 minutes. So now in the .ini file uh, of the Arduino IDE, you are required to have two functions. One is setup function. You are required to write two functions. One is void setup and the other is void loop, right? So in the void loop, what you do is that let's first talk about void setup. The thing is, first before talking about the body of this function, let's talk about their like difference between them. The setup function, it is executed only once, right? And the sequence is that first the setup function will be executed and then the control will go to the loop and this the body of this loop will execute forever. Okay. So let's first talk about the body of the setup function. So here we are initializing the serial communication. And again, you don't need to worry about that, but make sure that if you are running this example in your Arduino IDE, include this file, include this line. What this line is doing, we will talk about later in somewhere at some other point in the course, not at this point. Okay. Okay, now here we are calling the function read two-digit values. Which function? Which we have defined already in .ini file. So what is the sequence? First we define this one, these include these lines, then we define this function, then we have this void setup function, and then we have void loop. Okay. So now void setup function is calling the read two-digit value. So it will basically read two-digit value from your console and it will put it in the val1, right? Let's say that two-digit value was 23, right? Then you are calling the same function again to read another two-digit value and put it in the val2. What is val2? Remember, it is the variable which we have defined in our assembly function, in our assembly file, right? But this code which you are currently seeing is in the C file or .ini file. Let's say the second value you provide is 24. So that value will be put in the val2, right? And then you are calling the assembly code compute. Remember, we have written this code in the assembly file. And what will this code do? So it will get the values from val2, put it in R18, get the value from val1, put it in R19, add the two values together, put the result back in val1, and then return, right? So here this compute is called. So now after the compute is executed, we have the sum of 23 and 24 in val1 memory location, right? And then we are saying after compute the value is print val1. So on your console you will see the message after compute the value is whatever sum is 23 plus 24 which is 47. Okay. And what we have in the body of the loop, it is we are simply saying once. So first this will be executed, right? And after that, this loop function will be executed forever, which will actually do nothing but will wait for these number of time units like 20,000 milliseconds, which mean 20 seconds, and then after every 20 seconds, it will print a static on the console. Then again wait for 20 seconds and print the static on the console and so on. Any questions? Now, after this example, I expect you to understand that what is the job of these directives dot common, dot equate, dot set, dot global, and how we can refer the variables or the functions which are defined in assembly language, how we can refer to them from a code which is written in the C language in .inf. Okay. So with that, let me stop here. Go ahead and do your quiz. I'm here until end of the quiz. If you have any questions, please feel free to ask. Okay.